All right, so with the connection, we establish an affine connection on the Riemannian manifold. Then we can use this to define a connection on the tensor bundle writ large. And the way that we do this is essentially by first defining the covariant derivative of a covector field. And the way to define the covariant derivative of a covector field is it produces a new covector field, and we essentially want to use the parallel transport maps. Okay, so recall that the covariant derivative of a vector field, y in the direction of a vector field x, is given by this parallel transport structure, where essentially we take the limit. If we take a curve, let's take a curve gamma, which starts at the point P, and such that gamma prime of 0 is equal to xp. And now we have the parallel transport structure induced by the affine connection, but we're going to assume that we have the parallel transport structure. So we have an isomorphism between the tangent space at gamma of 0 and the tangent space at gamma of t. All right? And now we can use this isomorphism to establish an isomorphism between the cotangent space at gamma of t and the cotangent space at gamma of 0. Namely, I send a one form at gamma of t to a one form at gamma of 0, which takes in a vector at gamma of 0, and the output is the covector at gamma of t evaluated at the on the vector, which is the parallel transport of the vector at gamma of 0 to gamma of t. Okay, so basically I can define a every isomorphism between the given by the parallel transport structure between the tangent space at gamma of 0 and the tangent space at gamma of t of our manifold induces an isomorphism in the opposite direction between the cotangent spaces from the tangent space at gamma, or the cotangent space at gamma of t to the cotangent space at gamma of 0. So we can use this to define the covariant derivative of a one form as essentially the limit as t let's say as t approaches 0 of the parallel transport of the covector field evaluated at gamma of t, the parallel transport of that covector to gamma of 0, a covector at gamma of 0, minus the covector field evaluated at gamma of 0, all divided by t. We take that derivative, and that's going to give us the covariant derivative of the one vector. Okay, or sorry, the covector. Sorry, 1 second. I gotta focus on changing lanes here. Okay, so now we can show by using computations and using the we know that the original affine connection determines a formula for the original covariant derivative of a vector field is given by also a formula from the parallel transport structure. Namely, it's the limit as t approaches 0 of the inverse now of the parallel transport map from gamma of 0 to gamma of t, parallel transported the vector at gamma of 0 minus the vector field evaluated at gamma of t all over t, I believe. Is that correct? No, that's wrong. Sorry. We take the, so the covariant derivative of a vector field y in the direction x is also defined by the parallel transport structure. Namely, we take the limit as t approaches 0 of the parallel transport from t to 0, basically from gamma of t to gamma of 0 along gamma, which is the inverse of the parallel transport from 0 to t along gamma. We take that of y evaluated at gamma of t. So we parallel transport y evaluated at gamma of t back to gamma of 0, and then we subtract y evaluated at gamma of 0 and divide that by t, right? And that gives us the covariant derivative. That gives us a formula for the covariant derivative of a vector field. We can use that formula to and go back and forth between the parallel transport structure and the covariant derivative itself to establish a formula for the covariant derivative of a covector field. Okay. And one quick side note before I state that formula is that you should remember that the parallel transport structure and the affine connection determine each other. Basically, you can specify one or the other. And the way that you go from specifying a covariant derivative, which basically means you give the Christoffel symbols in local coordinates, is one way to specify a covariant derivative or an affine connection. So the way you go from that affine connection to the parallel transport structure is through differential equations, where essentially to parallel transport, you require that the covariant derivative along gamma prime of t of the vector field that you're differentiating, say y, is identically equal to 0. And then in local coordinates, that will reduce to a system of differential equations, which is actually linear with respect to the coefficient function of the vector field. So it's a first order homogeneous system of differential equations. And you can use the Picard-Lindelof theorem from differential equations to guarantee local existence and uniqueness. And then you can use a compactness argument, actually, because the geometric curve gamma is assumed to be compact in the manifold. You can use a compactness argument to actually get existence and uniqueness of the global parallel transport. Okay, so that's how you can determine the parallel transport structure from specifying the affine connection. Okay, so now the formula for the covariant derivative of a covector field against a vector field x. So like del or nabla sub x of omega is going to be given. It's the one form, and it's a one form which, if we evaluate this one form on a vector field y, it's given by the vector field x so x of omega of y, so x omega of y basically, plus or minus omega of the covariant derivative of y with respect to x. I think it's a minus sign. I'm almost pretty sure it's a minus sign. So so that's correct. So it's the covariant derivative nabla sub x of omega is equal to x omega of y minus omega of nabla x y. So essentially, we take the we differentiate the function, the c infinity function, omega of y. We differentiate that function with respect to x, and then we subtract omega evaluated on the covariant derivative of the vector field y with respect to x. Okay, and this gives us a way to take the covariant derivative of a covector field in a canonical way given an affine connection or a way to take the covariant derivative of a vector field. Now, once we have a method for differentiating vector fields and covector fields, all of a sudden, we can take the covariant derivative of any tensor field. Okay, and how do you do this? Well, you essentially use the parallel transport structure, right? So again, you just define the parallel transport of a tensor, and right, we have a way to parallel transport vectors. We have a way to parallel transport covectors. We can also parallel transport tensors. Okay, so how do you parallel transport a tensor? Well, if we think about how do you parallel transport a tensor? Yeah, so you essentially want to, so the tensor field is a smooth section of the tensor bundle, um, and since we can parallel transport vectors and covectors, this gives us a natural way to parallel transport the basis for the tensor bundle, simply by sending some basis vector to the component-wise. So essentially, if we look at the tensor bundle, right? If you look at the algebraic definition, it's a unique vector space such that every multilinear map from the Cartesian product of, let's say, R copies of the tangent bundle and S copies of the cotangent bundle, every multilinear map from that Cartesian product into our base field, let's say the complex numbers, factors uniquely through the tensor product. And so we just need to define a parallel transport structure on the Cartesian product, and we can just do that component-wise. We can just component-wise parallel transport the vectors and covectors in the Cartesian product of the tangent/cotangent bundles, and then factor that through to the tensor bundle. Okay. When I say factor that through, I would just say that there's a projection mapping from the Cartesian product into the tensor bundle, which sends, an n tuple of r plus s tuple of r vectors and s covectors to their tensor product, where you just take the tensor product of the components. Okay, so that will give us a way to parallel transport tensors, and then we can use that parallel transport structure to define a covariant derivative of a tensor field with respect to a vector field X in the same manner. And then now, with that being said, we can derive the formula using the definition of the covariant derivative of a vector field and the covariant derivative of a covector field in terms of the corresponding parallel transport maps between the tangent spaces and the cotangent spaces. We can use those parallel transport structure formulas to determine the formula for nabla x of t, where t is an RS tensor, in terms of the covariant. We can write that in terms of the covariant derivatives of the vector fields and covector fields. And so this is the formula. If we have, so let's just look at, so an RS tensor, it's going to, the input is going to be R covectors and S vectors, right? If we take the input of this tensor, So, right. So the covariant derivative nabla x of t evaluated on, let's say, r covectors omega 1 through omega r, and s vectors x1 through xs, or sorry, y1 through ys. Let's say y1 through ys, because we're taking the derivative against the vector field x. This is going to give us a new RS tensor, which is given by, so first you take the derivative x, so just x, of the function t, evaluated on these r covectors and s vector fields. We just take x of t of omega 1 through omega r, comma y1 through ys, and then we subtract the sum of the tensor t evaluated on the sum over I of essentially the tensor t evaluated on the r covectors and the s vectors, where the ith covector is replaced by omega I is replaced by nabla x omega I. Okay, and we take the sum over I, and then we also subtract the sum over j, let's say, of the tensor t evaluated on the r covector fields omega 1 through omega r, and then the s vector fields y1 through ys, except for the jth vector field is yj is replaced by nabla x yj. Okay, so hopefully I explained that formula correctly. That is the formula for how to take the covariant derivative of a tensor field, which is just induced naturally by taking the covariant derivative of a vector field. Okay. All right. So we can differentiate tensor fields, and this gives us a way to determine. This gives us basically a formula for taking the covariant derivative of a vector field. This also gives us a formula for taking a differential equation for taking the parallel transport of a tensor field. Okay. Now, turns out that, what else should I say about this? So I'll make some more comments tomorrow, but there is an important section about the Hessian, which is essentially if you take the nabla, if you view the nabla operator as actually sending instead of viewing, okay, let's just look at the covariant, so instead of viewing the nabla operator as a map from the smooth sections of the tangent bundle cross the smooth sections of a vector bundle to the smooth sections of a vector bundle, okay, so instead of viewing it in that way, where you send like x comma t to nabla xt, where t is a section of a vector bundle. In the cases we've described, t would be a section of a tensor bundle, and x would of course be a vector field. So instead of using that notion of nabla, you can also use the notion of nabla as a map from the vector from the set of smooth vector fields. So the set of smooth sections of the tangent bundle. Or sorry, no, sorry. You can view nabla as a map from the set of sections of the vector bundle E to the set of sections of the cotangent bundle cross E, basically. Is that right? I don't know if that's exactly correct, but you essentially want to send, right, you want to send a section of the vector bundle E, let's say S, to to a section of the cotangent bundle cross the vector bundle E, omega comma nabla s, where the input is a vector x and a okay, let's not talk about this in terms of vector bundles per se. Let's just talk about it in terms of the tensor bundle. So you want to think of nabla as a map from the RS tensor bundle over the manifold into the RS plus 1 tensor bundle of the manifold, where, that extra 1 component, we have an extra component of the cotangent space. We have an extra cotangent space, basically, and that takes in an extra vector, and the vector that it takes in is exactly the vector field that it takes in is exactly the direction with which we take the directional derivative. So we're going to get this nabla operator sends a tensor T to a tensor nabla T, which is an RS plus 1 tensor, where the final argument, so the first R arguments are going to be R covectors, the next S arguments are going to be S vector fields, and then the final argument is going to be a vector field, and the input argument is the final input argument is a vector field, and this is defined by the final input, let's say, is a vector field X. We define this by saying that's equal to nabla xt of the first R plus S inputs of the tensor. Okay, so we get a map which sends an RS tensor field to an RS plus 1 tensor field. It sends T to nabla T, where the final input of nabla T is the vector field which determines the direction which we're taking the directional derivative. When we view the map like this, then we can define the Hessian. And the Hessian is essentially the square of this operator, so it takes an RS tensor to an RS plus 2 tensor. And it turns out that if you require that this Hessian, so you can calculate the formula for the Hessian, and I can state it for you real quick, just because I have the notes here. So the formula for this Hessian function is going to be essentially so this nabla squared T, the final two inputs, let's say the first RS inputs are just R covectors and S vector fields, and then the final two arguments are two vector fields x, y, and we have that this nabla squared T of ... comma xy is equal to nabla y of the RS plus 1 tensor nabla T, evaluated with the final input being x, and this is equal to, just by definition here, that's just by definition of the first nabla operator, this is equal to nabla y nabla xt minus nabla of t in the direction nabla yx. Okay, so let me just state that in words. We have the covariant derivative in the direction y of the covariant derivative of the tensor field T in the direction x minus the covariant derivative of the tensor field T in the direction of the covariant derivative of the vector field x in the direction y. Okay, so again, this is the Hessian. So nabla squared t is now an rs plus 2 tensor. And if we set the final two arguments to be x and y respectively, the first r plus s arguments are r covector fields, s vector fields. If the final two arguments are x, y, then this Hessian operator, nabla squared of t, boils down to nabla y nabla x t, evaluated on the r plus s components, minus nabla sub nabla yx of t. Okay, so evaluated on its components. So we have the Hessian of t of dot 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 comma x comma y is equal to the covariant derivative in the direction y of the covariant derivative in the direction x of t minus the covariant derivative of t in the direction of the covariant derivative of x in the direction y. Okay, so let me just show you the picture here. This is the picture here. So the Hessian matrix is t dot 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 xy is given by this formula nabla y of nabla t dot 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 x. Okay, so this is just evaluating the definition of this nabla operator on the final argument, and then we apply the rule for we apply the rule, but essentially the rule for what it means to take the derivative, the covariant derivative of this tensor field nabla t in terms of the tensor field t itself. Okay, so we first evaluate this. We first evaluate the tensor field on this final argument here. So we take the covariant derivative with respect to actually this this tensor field being evaluated at its final argument, and then we subtract the covariant derivative in the direction of nabla y added to this input. So we actually take the covariant derivative of the input vector field and evaluate the and then evaluate this nabla of t on that input, and by definition that's just nabla in the direction of the input vector field. Okay, so let me just show you the missing step here. Missing step is here. Basically, this nabla y of nabla t comma x is we have this nabla y nabla xt minus nabla t of nabla y evaluated on the input. And then, of course, this, by definition, is just the covariant derivative of the tensor field t in the direction nabla y of x. Okay, so this is the Hessian. Okay, turns out that this is not the Hessian. This is the second. This is just the nabla squared operator. If we just put this operator on a 0, 0 tensor, so if we actually just apply this operator to a 0, 0 tensor, which is namely a function, then we get a 0, 2 tensor, and called the Hessian of f. Okay, and the 0, 2 tensor you can see is just given by this formula here. We have nabla y df of x, which is equal to yxf minus nabla yx of f. Okay, so this is the Hessian of f evaluated on the vector fields x and y. And the important thing is when we require this Hessian, then we end up with the condition that the torsion must vanish. Okay, so it turns out that if you take the if you look at the antisymmetric part of the Hessian, nabla squared f of x comma y minus nabla squared f of y comma x, if you look at this basically the part of the Hessian which doesn't commute, then you actually get, by definition, you actually get the torsion acting on f. Okay, so this is really important, and so we can require for the Hessian to be symmetric that quote unquote partial derivatives commute. A lot of people say, like in differential geometry, what we want out of a Levi-Cevita connection is the partial derivatives to commute. That's kind of the more general notion of that is requiring the Hessian to be symmetric, right? That's kind of the more like it's like a more coordinate-free way to say the partial derivatives commute is saying the Hessian operator is symmetric. Okay, if we require the Hessian operator to be symmetric, that's equivalent to making the connection torsion-free. So to setting the torsion equal to 0. Okay, So then there's a second thing that we want, which is called metric compatibility. Okay, so metric compatibility is essentially requiring the metric tensor to be parallel, which means fully parallel, not just parallel along a curve. That means that the covariant derivative of the metric tensor in any direction is identically equal to 0. Okay, and this is equivalent to requiring that essentially the covariant derivative, or sorry, this is equivalent to requiring that if we take um, um, three vector fields x, y, and z, then we have that x of the inner product of y and z is equal to um, the inner product of nabla x y comma z plus the inner product of y comma nabla x z. Okay, so essentially we get a product rule with the covariant derivative. If we take the derivative of an inner product of two vector fields against a third vector field x, we get a product rule essentially with the covariant derivative, and that looks physically like